Hello everyone, my name is Erol Bicher and I'm a PhD candidate in the Nuclear Thermohydraulics Engineering Laboratory at the Department of Nuclear Engineering in Seoul National University. And today I will be introducing you my research work, which is about the dynamic bubble size modeling for post-scrubbing codes. This is the content of my presentation. I will first give details about the multiphase flow dynamics, and then I will continue with the correlation development, implementation, and validation. Then I will conclude this presentation. The phenomenon that I'm interested in is pulse scrubbing is quite relevant in conventional nuclear power plants as well as the small modular reactors. In pulse scrubbing, when there is an accident in a nuclear reactor, steam, gas, and fission fragments are collected and run through a large body of water where the fission fragments are scrapped and releasing to the environment is blocked as a safety measure. And this is assessed by a figure of merit called decontamination factor, which is basically how much mass enters and how much exits the pool. And this decontamination factor is calculated and predicted by lump parameter pool scrubbing codes and generally underestimates the decontamination factor due to heavy assumptions and using of empirical correlations. I would like to introduce to the IPRESCA outcomes. IPRESCA is an expert group that comes together and discuss the post scrubbing and source term calculations. One of the main outcomes of this last year's meeting was using the CFD modeling to introduce new correlations to the post scrubbing codes, which will be done in this research. Once we look at the post scrubbing experiments since from 1966, we can see that the hydrodynamics is one of the least studied processes in post scrubbing. Despite in the post scrubbing manuals clearly indicate that hydrodynamics such as bubble size and shape is quite essential for the calculation of the decontamination factor. And if you look at the post scrubbing codes, we can see that bubble size is used as a constant diameter in the swarm region for in post scrubbing codes. So in order to improve this, a general framework that was proposed in the IPRESCA meeting will be used to use the CFD analysis to generate more data to drive a correlation and implement into a post-scrubbing code, which will be done for the bubble diameter modeling to improve the post-scrubbing codes. If you look at the previous studies for the 3D modeling of high inlet velocity gas liquid flow, which is quite different from the general pipe flow. The researchers, they used a volume of fluid or constant bubble diameter models, which both of them have discrepancies such as having a high computational cost or not being able to capture the flow variables. However, this study uses interface layer transport technology coupled with mixture K-epsilon turbulence modeling to have a practical modeling framework to calculate the flow variables for various experiments. Another thing that was done during the research is to propose a new correlation, as can be seen in here. And if you look at the previous correlations, they are rather have application ranges are quite narrow, and then they're relying on other correlations to calculate parameters such as energy dissipation rate and relative velocity, which contributes to overall uncertainty of the correlation itself. So the correlation that was proposed as a result of this research has a higher range, and also it calculates varying diameter along the pool, which is not available in other correlations. And if you look at how the bubble diameter was utilized in the pool scrubbing studies, one approach is to use a constant diameter from a correlation. The other one is using a constant diameter that was obtained from an experimental data. And the third one is the log normal distribution if you have the entire experimental data. However, these things are not always readily available. Therefore, this present study is within the code itself. The code handles the calculation of bubble diameter for the hydrodynamic conditions using the hydrodynamic conditions that automatically calculates the decontamination factor. And implementation led to increase of the decontamination factor, which helps to reduce of the underestimation factor. And in the previous correlations, there was constant diameter used, and in this correlation, we have a varying bubble diameter along the pool streamwise direction, which is implemented into a post-scrubbing code. And to introduce the research objectives are already introduced as can be seen in here, but the general research purpose of this study is to enhance the overall safety and efficiency of advanced nuclear reactor containment systems by introducing a new bubble size model for the pulse scrubbing in the swarm region, which each research objective corresponds to one limitation or unresolved issue from the research. The first one is calculating the two-phase flow, and for that I have used 3 experiments with different inlet conditions, and the research corresponds to a global regime that was designed for example, station blackout conditions in nuclear power plants. And 3D computational CFD modeling was done using OpenFOAM, and it's Eulerian simulation, which introduces the calculation of turbulence modeling as well as interfacial phase modeling. And for the bubble diameter, I coupled interfacial transport equation with a two-fluid model, which has one source term, which is turbulent impact, and 2 sink terms for the coalescence. And then it calculates the interface area concentration, which then can be used to calculate the bubble diameter. As for the turbulence modeling, an iterative approach was proposed to calculate the inlet turbulent kinetic energy and energy dissipation rate. As for the phase interaction modeling, 4 forces were identified as crucial for the calculation, especially drag and lift force. And in the lift force, the lift coefficient changes sign because there are larger bubbles available in the domain. These are the domains and computational settings. One thing should be remembered that this research is constrained by 2 things. One is the critical Weber number, which should be less than 10 to the 5, and the other is the bubble flow, where the central maximum void fraction should be less than 25%. This one shows an animation of the simulations. As we can see, the classic bubble column behavior can be seen, and for higher velocity cases, there's more like a column. However, in lower velocities, there's more like a variable bubble column behavior. Flow variables were captured quite well with the experiment for both experiments in here, and the bubble diameters were calculated quite accurately with the experimental data using the proposed methodology. And using this, now that the flow variable and the bubble diameter is calculated correctly, now can be used to propose a new correlation. This correlation has a function of the inlet turbulence injector Weber number, inlet turbulent intensity, and the aspect ratio of the system. And using this, the experimental and the simulation data with the multiple variable regression analysis, with the data, this correlation is obtained. And once tested, it was found that the correlation has 3.3% average error and 14.1% maximum error, which is quite reasonable. And this correlation also was tested with other correlations, namely Hibiki and Ishii and the Azimi correlations, which can be operated in similar operating ranges. It was found that with the average error, the present correlation has the minimum average error, which makes it quite robust and useful for these kind of conditions. And the methodology is implemented into pulse scrubbing codes. In the current models, the red bubbles that can be seen here in the swarm region are constant diameter, and there's in the vent exit region, the contamination factor is calculated using various processes as well as the swarm rise region. And a new bubble size model was implemented to calculate the turbulent intensity and the maximum bubble diameter so that it can calculate the bubble diameter for each section so that the bubble diameter can be assigned to certain sections and continue. One assumption was made to include a flow because turbulent intensity is calculated using an iterative approach, there is a chance that the maximum iteration can be reached. Therefore, if that were to happen, the code calculates the turbulent intensity using a pipe flow approach. However, in all the test cases that we have performed, it was never happened. And as for the bubble swarm rise region, when at the current pressure, the volume of the total volume of the bubbles are calculated, and then the diameter is calculated, and it was compared with the current assigned diameter, which helps to calculate an expansion ratio. And using that, the bubble number density has been changed to account for the average bubble diameter that was calculated from the correlation. And using that, we can continue with the correlation for each time in every section. When the height is increased, the new bubble diameter is calculated, and then new bubble number density is assigned. And this was implemented into pool scrubbing code to see two experiments were selected considering data availability, LASA and FNC. Similar practices were applied for the normalization, and the steam, gas, and aerosols were injected here to have pool scrubbing in this volume. And first, the default model was cross-validated from the literature to find the correct results. And then the implemented new bubble size diameter was assessed to compare with the default bubble size diameter. And an average percent increase of about 45% in the decontamination factor has been found. And the same thing has been done for the FNCP experiment, although the decontamination factor results are relatively lower here because the decontamination factors are generally lower. And overall, in total, about 36% of increase in the decontamination factor results were obtained from both experiments. Which brings me to the summary and the major findings. To summarize, and a tailored interface air transport equation coupled with two fluid model to introduce the best practice and guidelines for turbulence and turbulence method and the interfacial forces to obtain the flow variables and the bubble diameter results. And using that, with the experimental data, a new correlation was proposed that accounts for the bubble size reduction along the pool here with an approximately 5% of average error. And using that, it was implemented into a pool scrubbing codes. It was found that the bubble size diameter works quite well with the new methodology, with an increase about in the decontamination factor calculation about 35.89%. And as for the future work, it will be quite beneficial to identify the boundaries of the swarm region to account for a wider range of data, especially in flowing at velocities. And of course, there are other parameters that can affect the contamination factors, such as residence time and rise velocity, which can be also studied to propose correlation in a similar manner. And also implementation of one group and two group interface air transport equation to pool scrubbing codes and OpenFOAM directly would be quite beneficial. These are the research-related publications, and thank you very much for your listening.